Right now, trillions of invisible particles are streaming through your body. They move at nearly the speed of light, and they are so ghostly that they could pass through a wall of solid lead a light year thick without hitting a single atom. But we didn't discover these particles by seeing them. We discovered them because the math of the 1920s demanded they exist. Physicists were studying a process called beta decay, where an unstable atomic nucleus spits out an electron to become more stable. By measuring the initial and final states of the atom, they could calculate exactly how much energy that escaping electron should carry. But every time they ran the experiment, the electron emerged with a random, lesser amount of energy. The energy was missing. In physics, energy cannot simply disappear. The law of conservation of energy dictates that energy is never created or destroyed, only transferred. If the math on beta decay was correct, the foundational rule of thermodynamics was broken. In 1930, physicist Wolfgang Pauli proposed what he called a desperate remedy. He hypothesized that a tiny, invisible, neutrally charged particle was being ejected alongside the electron, secretly carrying away the missing energy. He was so sure this particle would be impossible to detect that he bet a case of champagne no one would ever find it. Shortly after, Enrico Fermi formalized Pauli's idea. He named the hypothetical particle the neutrino, Italian for the little neutral one, and wove it tightly into the mathematics of a newly defined weak nuclear force. The math worked perfectly. But fixing the equations on a chalkboard left the scientific community with an immense physical burden. To prove their models of the universe were correct, scientists now had to build a machine capable of catching a ghost that actively avoids interacting with matter. By 1956, physicists Frederick Reines and Clyde Cowan realized that since the probability of catching a single neutrino was effectively zero, they needed an overwhelming swarm of them to have a chance. So they hauled a 300-liter detector to the Hanford nuclear site in Washington, placing it right next to a massive fission reactor pumping out trillions of neutrinos a second. This diagram illustrates their trap, a process called inverse beta decay. The detector was filled with water, heavily loaded with protons. The idea was that out of trillions of neutrinos passing through, a few would inevitably crash head-on into a proton. That collision forces the proton to transform, spitting out a positron, which is the antimatter version of an electron, along with a neutron. This reaction produces a highly specific signature. The positron immediately annihilates with a nearby electron, creating a flash of gamma rays. Then, exactly half a microsecond later, the wandering neutron is captured by a nucleus, creating a second gamma-ray flash. Those two distinct flashes, separated by a fraction of a microsecond, are the fingerprint of a neutrino. After months of filtering out background radiation and cosmic rays, the detector registered about 3 of these double flashes per hour. Reines and Cowan sent a telegram to Wolfgang Pauli confirming the detection. As a result, Pauli happily bought the champagne. Catching the neutrino proved that the law of conservation of energy held strong, but it also exposed how little we knew about the subatomic realm. In 1962, a team at Brookhaven National Laboratory began questioning the assumption that all neutrinos were identical. They knew that decay processes involving different particles, like heavy muons, also produce neutrinos. They wanted to see if the neutrinos born from muons were exactly the same as the ones born from electrons. To test this, they used a particle accelerator to create a high-speed beam packed with both muons and neutrinos. Then they fired that beam at a wall of steel made from 5,000 tons of scrapped battleship armor. The dense armor was designed to stop absolutely everything except the penetrating neutrinos, which passed straight through into a neon-filled spark chamber. This graphic compares the 2 expected outcomes inside the spark chamber. If all neutrinos were the same, striking an aluminum plate in the chamber would produce short, jagged sparks, the signature of an electron. Instead, the team observed a long, straight path. That straight path was the distinct signature of a muon. The team, led by Leon Lederman, Melvin Schwartz, and Jack Steinberger, realized these specific neutrinos were hardwired to produce muons, not electrons. They had finally discovered the muon neutrino. This discovery revealed that neutrinos form a multi-generational family, with each flavor corresponding to a specific type of charged lepton. As the mathematical framework known as the Standard Model matured, it accurately cataloged the electron and the muon, along with their matching neutrinos. In 1975, physicists discovered a third, incredibly massive lepton called the tau. The math dictated that the tau must also have a corresponding neutrino. Finding it would take another 25 years. In the year 2000, the donut experiment, which stands for direct observation of the new tau, utilized the Tevatron accelerator at Fermilab. They needed the immense power of the Tevatron to shoot a high-energy proton beam into a tungsten block to generate these heavy tau neutrinos. The detection method was a modern refinement of old techniques. They placed plates of photographic nuclear emulsion behind massive shielding. As the tau neutrinos passed through, a tiny fraction would interact with the iron nuclei in the detector, creating new particles that left physical, microscopic tracks burned into the emulsion plates. This animation shows the exact signature they were looking for. Out of millions of events, the team scanned the plates for a track barely a millimeter long that suddenly snapped into a sharp, distinct kink. That specific angle was the visual proof of a tau lepton appearing and immediately decaying. They found 9 of them. Identifying that distinct kink verified the brief existence of the tau neutrino. The lepton family tree was complete, perfectly aligning with the predictions of the Standard Model. Over 70 years, the hunt for the neutrino earned multiple Nobel Prizes, proving that a desperate guess was actually a physical reality that dictates the structure of the Standard Model. This demonstrates neutrino oscillation. As they fly through space, neutrinos cycle between electron, muon, and tau identities. Because relativity dictates that only particles with mass experience time, this shape-shifting proves neutrinos possess a small, non-zero mass. Scientists now use giant underground detectors to harvest neutrinos as data. Because these particles are uncharged and virtually massless, they fly in straight lines from the heart of the sun or distant supernovas, passing through intergalactic gas and dust that would block light or radio waves. Pauli's theoretical fix for a math problem eventually gave us a new way to study the core of stars and the centers of collapsing galaxies, providing a view of the universe that light alone cannot reveal. If you want to explore more of the invisible forces shaping our universe, like this video and subscribe to the channel. Let us know down in the comments what mystery we should investigate next.